Let's look at example 5. So in this case, we have a drug that is a weak base with a pKa of 4.2. We're putting it intravenously into the blood where the pH is 7.2. Patient's a little acidotic, but we'll roll with it. And the blood comes in contact with a tissue that has a pH of 4.2. So maybe there's inflammation and we've got a relatively acidic pH in this tissue. So again, the question is, where's this drug going to go? Will it stay in the plasma? Will it move into the tissue? And effectively what we're trying to determine with this, we've got blood and we've got tissue. They each have their own pH. What direction is this going to want to move? Now, we know that in a more acid pH, this is a weak base, so it's going to be more ionized in that acid pH. And in a more alkaline or basic pH, this weak base will be more non-ionized. We also know that the point at which our N/I ratio is 1:1 is the pKa, which is 4.2. So as pH goes below 4.2, ionization will predominate. As the pH rises above 4.2, non-ionized state will predominate. Okay, so now the way we've been approaching these is that we look at the N/I ratio in each of these two components. So in our blood, we have a pH of 7.2. And so if we use our 10 to the pKa minus pH equals, now this is a weak base, so drop the base, the N, no, don't drop the B, drop the N. The N is going to be on the bottom. Some people actually use bin, so base is I over N, is what that stands for, which I think is quite handy. And otherwise we do the same thing as we did for the weak acids. So we have our pKa 4.2 minus our pH 7.2. It's going to give us a 10 to the minus 3 is I over N. And again, if you do this calculator way, you have 0.001 over 1, or you may be used to doing 1 over 1,000. Either way, again, remember that now the numerator is I. The denominator is N. So this is the opposite of what we had with our weak acid. So on this side, we've got for every 0.001 I, there's going to be 1 N. Or for every 1 I, there's going to be 1,000 N. As long as we keep those N's and I's separate, we'll be okay. All right, so that's one side of the equation. That's great. What about the other side? On the other side of this membrane, we have a tissue that has a pH of 4.2. Before we go any further, I hope that you've noticed pH equals our pKa. That's a special scenario. So we don't have to do any calculation on this side. We know that when the pH equals the pKa, that 50% is going to be ionized and 50% is going to be non-ionized. Our N/I ratio is going to be 1:1. Just by definition, that's what we're dealing with. Now, here's the thing. So for every 1 I, we've got 1 N. Here's a mistake that's very common for people to make. They see that pH 4.2, they think, oh, this is 1:1, and then they say, oh, 50% of the drug will be on this side. No, that's not how this works. Force doesn't work that way, Chewy. What that's telling us is that on this side of the membrane, the N and the I have reached an equilibrium, and that's going to be 1:1. For every 1 N, there's going to be 1 I. And for on this side, we've also reached an equilibrium. On this side, for every 1 N, there's going to be 0.001 I's. Or, can't erase that, or if we did it the other way, you may have, for every 1,000 N, there's going to be 1 I. Either way, again, it's the same amount. But we still have to compare these two compartments. And in order to do that, we need to simulate equilibrium, meaning that the N's have equilibrated with each other. that means the ends have to be equal. So if we set the ends equal to 1, then this is going to be the easier one to use. 1 to 1 on the tissue side, that's easy. You didn't even have to think about that. On this side, for one end, there's 0.001 I's. Let's just go back a quick step. Does that make sense? Go back to our basic initial premise that if this is a weak base with a pK of 4.2, this blood pH, 7.2, is far, far more alkaline than the pKh. So we should have more non-ionized than ionized. Is that true? Yeah. We've got one non-ionized for every teeny, 1/1000th of an ionized particle. So the N is the bigger number, so this is all matching with what we know the way the world works. So now that we have our N's equal to each other, and we know that when each of the N's is 1, what their relative I's are going to be, same idea. This is almost negligible, so we don't even really have to worry about it. So we're really talking about 3 parts here. We're dealing with 3 parts. At any given time, we've got 1 part that is non-ionized in the blood, 1 part will be ionized in this tissue, and 1 part will be non-ionized in this tissue. 1, 1, 1 gives us 3. Now, what we want to do with that, pretty much, again, we always are going to want to ask how much total is in the blood compartment? How much total is in the tissue compartment? So in blood, we know we're going to have 1 out of 3, about 30%, or 33%, I guess, 1/3. And in this tissue compartment, we're going to have 2 out of 3, about 67%, 2/3. And just like we did in that last example, we could take this a bit further. I can only erase the most recent things that I've written. But we could take this a little bit further. So if we said that in our blood we have approximately 33% at equilibrium, and in our tissue we have approximately 67%. Well, again, what if we gave a specific amount? What if we gave 300 milligrams of drug? What we're really saying is that about 100 milligrams would be still staying in the bloodstream. About 200 milligrams would have moved into tissue. It's relatively going to want to move into the tissue. Not quite as thoroughly as some of our other examples, but this favors movement of drug into the tissue, distribution of drug from the bloodstream into the tissue. Does that make sense with the basic premise that we know about how drugs are going to behave based on ionization? The blood, in this case, is a more alkaline pH, so we know that this weak base will be more non-ionized and can freely move out of that environment. When it gets into this tissue, that's relatively more acidic, is going to be trapped and can't move back. So the net movement is going to be from the alkaline, from the like, to the acidic, to the unlike. And so that's what we're seeing here, from this more alkaline plasma into this more acidic tissue. So weak bases are going to tend to get trapped in more acidic tissues. So hopefully that has clarified this example. And again, if you have any questions, you know where to find me. Thanks.